Hi. Before we begin with gases, I'd like to give you a word of advice. Don't do what I did when I was an undergrad, okay? We began with gases on a Friday. We went through a bunch of equations, and trying to be a good student, I spent the whole weekend memorizing the equations, memorizing the names of the laws. Come Monday, I go to class, and the first thing the professor said is, you don't need to know all these formulas. You don't need to know these equations. Are you serious? I spent the whole weekend memorizing it. So as we go through the different parts of the chapter, I'm going to give you an equation and I'm going to tell you, but don't memorize it yet. Don't do, wait until the end. Names for the different laws is up to your instructor. I tell my students, don't memorize the names. I don't mean it disrespectful. I just don't see the point of memorizing names. That's history. If you're taking history of science, yes, you want to know all those names. If you're taking chemistry, to me that is trivia. But the formulas, don't. You're going to memorize one formula at the end, and what I'm going to do my best is to show you that if you know that one formula, you can deduce all of the other ones very easily. So we minimize the memory work and instead we replace it with understanding. That makes your life a million times easier, I promise. So we talked about gases at the beginning. We said that it was a state of matter. The gases take both the shape and the volume of the container. Gases are important because we live surrounded by gas. The atmosphere is a mixture of gases and all of that. And also gases are very familiar to us on everyday life. In fact, I'm going to tell you many times, rather than memorize what happens when you do this, when you do that, try to think on an everyday example you can remember, and it will save you from memorizing. But gases were also very important in the development of chemistry, because if you remember, for centuries, all we had was alchemy. There was no real science. Gases were very easy to study, and we're back into the 17th, 18th century, but they were very easy to study. It was the first time that they were able to come up with a mathematical description of how matter behaves and all of that. So really, they were the beginning of real chemistry. Okay? When we deal with gases, it's going to be important to know the temperature, the pressure, how much obviously, and the volume. Okay? You already know what temperature, amount, and volume is. We will spend a bit of time talking about pressure. And we're going to use a very simple model and use it to analyze experimental data. In the next video, we are going to say, okay, this is fine, but how does it apply to real gases? What is the difference between the model and the real gases? And we're going to find out for most of the chemistry, you can use this model. It's not going to make a significant difference, okay? But first, let's talk a little bit about pressure. Pressure in physics is known as the force exerting on a given area. Why can you walk over on snow if you use snowshoes? Because the force exerted on the snow is your weight. If you are comparing maybe your foot versus the snowshoe, obviously the same weight is distributed over a bigger area, so you put less pressure. That's why you don't sink, excuse me, in the snow. When we talk about gases, gases is force exerted in which area? Most of the time we're talking about the walls of the container. Okay? So the gas molecules are in constant motion, they're here in the walls of the container, that is the pressure of the gas. When it comes to units, gases can be a pain, okay? Because it's like every branch of science uses different kind of units. Originally, the pressure was measured with a barometer, mercury barometer, so the first unit of pressure was millimeters of mercury. To make a long story short, this fellow Torricelli had a 1 meter tall tube filled with mercury, so the columns weighing down but the atmospheric pressure is pushing down. When both forces equalize, the mercury stabilizes. And he had graduations in here, so he was able to read how many millimeters of mercury was the atmospheric pressure. Okay? Some people hate to use that name because some people are obsessed with honoring the people who discovered something. So they said, we ought to call this unit Stor instead of millimeters of mercury in honor of the fellow who invented the barometer. His name was Torricelli. The only thing I want you to remember, because one thing that you're going to find out is that the problems come from many different sources. We are at the edge between physics and chemistry, so different people are going to use different units, and you're going to have to do conversions. But this is very easy, because 1 millimeter of mercury is 1 torr. So you get a problem when they give you the pressure in torrs, or you just change the units. No problem. The most common unit that we use in chemistry is going to be the atmosphere. 1 atmosphere is what is considered the normal atmospheric pressure. It's at certain temperature, sea level, blah, blah, don't worry. But 1 atmosphere equals 760 millimeters of mercury. So problems that come from experiments done by physicists are probably going to be given in, the pressure will be given in millimeters of mercury or in torrs. In chemistry, we're going to use atmospheres. The conversion is very easy, but you do need to know that conversion. Okay? The SI unit for pressure is the Pascal. If you ever need it, and there are very few programs that use Pascals, but if you ever need it, they will give you the conversion from Pascals to atmospheres. And like I say, other branches use different things. For instance, if you're talking about the weather, the atmospheric pressure is measured in bars and millibars. If you're looking at the pressure of your tires, you look in PSIs. So, like I said, every branch of science uses a different unit. We are going to use mostly atmospheres and sometimes millimeters of mercury. Okay? So, what is the atmospheric pressure? The atmospheric pressure is the weight of the column of air that is on top of an object. Okay? So, obviously, the height of that column is going to vary with the altitude. Think about if we're carrying the Earth, you have maybe the beach, and then you have a mountain, comes down, and the atmosphere maybe reaches up to here. The person at the beach has a very tall column of air. The person on top of a high mountain has a very small one. So the atmospheric pressure is smaller at high altitude than it is at low altitude. Have you ever seen some of those prepackaged food that they had cooking directions and it says high altitude directions? On many cookbooks, we have a recipe and then they give you the high altitude direction. Why? Because the atmospheric pressure is different, the water boils at a different temperature, so you need to cook at different time, and someone has calculated what is the correct times, so you get those variations in recipes and all of that. We don't notice atmospheric pressure. You're not aware of the weight of the water, of the weight of the air, sorry, but you do notice when it changes. Okay? When you take off and land in an airplane, you can feel that pressure in your ears and that pop. When you dive, you're going to feel the change in pressure. By the way, when you take off, how do you avoid that pressure in your ears? You swallow. This is no biology, I understand. But you have the eustachian tubes that connect your middle ear to your throat, and they equalize the pressure on both sides, but they're collapsed. When you swallow, they open, and all of a sudden the pressure inside and outside of the ear are the same, and you just don't feel that. Okay? So we're going to start looking what happens when you change one factor, what happens to another one. So the first example, you have a gas in a rigid container, so it cannot change the volume. It's sealed, so it does not change the moles of gas, but you're going to be heating that. You put in a hot plate, and you increase the temperature in the hot plate, notice the pressure increases. Okay? So when the temperature increases, the pressure increases. I told you with this chapter, I like to find everyday examples. What happens to the pressure on your tires when you drive for a long time? It goes up. You know, newer cars, you can read the pressure of your tires when you're sitting behind the wheel. And I remember my daughter bought a car, and she called me one morning. It was January, it was very cold, and she said, the pressure on my tires is low. Well, how low? It was just below normal, okay? Not very much, one, maybe 2 psi's. And are you still in the parking lot? Yes. Don't worry. Go on to work. Well, first I asked her, all 4 tires? Yes, it's all 4 tires. That's perfectly normal because it's cold. Now, go to work. When you get there, call me back. Well, she had like a 30-minute drive to work, and when she got there, she called me back and said, the pressure is normal. I told you, the friction of the tires against the road heated up the air and raised the pressure. Someone actually tried, I don't remember, and I didn't bother to that what gas was using here, but someone was measuring temperature versus pressure. They use pascals, but doesn't matter. Notice this is very important that they use Kelvin. Okay? Whenever you use gases, always use Kelvin. All of these formulas that we're going to be looking at, they work only when the temperature is in Kelvin. So remember, the degrees Celsius plus 273 is 273.15, but you can simplify that, gives you Kelvin, no degrees. So someone plotted temperature in Kelvin versus pressure, and notice that it made a straight line. Now, it got to a certain point where the temperature was so low, 200 Kelvin is very low, that you don't have gas anymore. The gas liquefies. Okay? So all he could do was extrapolate, but since you have a straight line, that was very easy, and they realized that if you reach 0 Kelvin, the pressure was 0. This is very important because 0 Kelvin is the absolute zero. It's the lowest possible temperature. I think it's probably been several months since the last time I checked. It has not been reached yet. Okay? We are getting very close, but we are going to see many reasons why probably will never be reached. Okay? But at 0 Kelvin, the molecules of the gas are not supposed to be moving at all, so they don't hit the walls of the container. The pressure is 0. So they put it in the form of an equation, and again I said, don't memorize it, not yet, okay? But the pressure is directly proportional to the temperature. And that's the Gay-Lussac's law. After who discovered, again, unless the instructor wants it, I don't worry about particular names. What happens with temperature and volume? Well, everybody knows that when you increase the temperature, the volume tends to increase. And another example is, look at the hot air balloon. When they first bring a hot air balloon, it's laying on the ground, they don't pump air into it. What they do is they start heating up the air, right? And as they heat up the air, the balloon starts swelling up, getting bigger and bigger and bigger, and eventually takes off. Why does the hot air balloon float? Well, remember, density is the mass divided by the volume. The amount of gas, the amount of air inside of the balloon does not change. But when you heat up the air, the volume increases, and you can see that if you've ever seen how they inflate those balloons. When the volume increases, the density decreases, and that causes eventually the density of the air inside the balloon is less than the density outside, and that causes the hot air balloon to go up. But again, if you've ever seen how they inflate the balloons, you can see that they're getting bigger and bigger and bigger, not because they're adding air, but because they're heating it. So once again, someone bothered to plot it, you get a straight line, and if you reach 0 Kelvin, the volume of the gas should be 0, which starts getting iffy because you're saying that the volume of the molecule should be 0 too. Okay? Like I said, that's why 0 Kelvin, most people consider, will never be reached. So once again, they come up with an equation. The volume is directly proportional to the temperature, Kelvin, don't forget that, it's essential. But as far as memorizing the formula, I said not yet, wait. Okay? And that's Charles' law after the fellow who did this work. How about volume and pressure? These are inversely proportional. So when you increase the pressure, you decrease the volume. And when you decrease the pressure, you increase the volume. The example I like to give you, imagine a syringe. Okay, and I'm very bad at drawing. And you're going to put your finger in here to stop it. If I pull the plunger, what happens to the volume? If I pull the plunger to the right, I'm increasing the volume. I'm decreasing the volume, right? And you're going to feel the suction in your finger. Why? Because the pressure here, if the volume, I'm sorry. When I pull the plunger, the volume increases. I'm used to always stand backwards, okay? You feel the suction. Why? Because the pressure decreases. That's how the syringe actually pulls out the liquid out of the bottle of medicine. What if I push the plunger towards the left? Now I'm decreasing the volume, but I can feel the pressure in the finger. In fact, if I let go, the plunger is going to go back to its original position. So volume and pressure are inversely proportional. If you graph pressure versus volume, you don't get a straight line. But if you graph 1 over pressure versus volume, then you get a straight line. And you'll find that chemists love straight lines because then you have an equation and you can extrapolate and you can do bad sort of things with that. We love straight lines. Okay? So once again, they come up with an equation where the volume and the pressure are inversely proportional. You are not going to memorize it yet. And that's Boyle's law. There's one more change we can make. Oh, before that, one reason Boyle's law is important because it explains how you breathe. Have you ever wondered what causes the air to come into your lungs and out of your lungs? It's not like you have a pump pumping the air in and out. What happens when you inspire? When you inspire, you contract the muscles. This is not anatomy and physiology, but basically you contract the diaphragm, you contract the muscle between the ribs, the diaphragm goes down, the muscles pull the ribs up. So what happens? You increase the volume inside of your chest cavity. If you increase the volume, we say the pressure decreases. So now the pressure inside the chest is smaller, not a whole lot, but it's smaller than the pressure outside, and the air rushes from high pressure to low pressure. So air comes into the lungs. When you exhale, you relax the muscles, the diaphragm and the intercostal muscles, right? So the diaphragm goes up, the ribs come down, the volume decreases. When the volume decreases, the pressure increases. So now the pressure inside the chest is a little bit higher than the atmospheric pressure, and the air rushes out. So that's why you use muscles to inhale and exhale, not to pump the air, but to change the volume in your chest cavity, because that changes the pressure and the air automatically moves. That's neat, isn't it? Like I said, there's one more change we're going to be doing, volume versus amount of air. Oh, come on. The amount of a gas is just proportional. The more gas you have, the higher the volume. Yeah, of course. Think on a rubber balloon, like they use for a party. Okay? It looks like that. You start blowing, and you keep blowing. The balloon keeps getting bigger and bigger and bigger. Why? Because you put more and more and more air. That makes sense, right? So once again, they came up with a formula that we are not going to memorize, and that's Avogadro's law. What did I tell you we're not going to memorize? Because we can combine them all together into what we call the ideal gas law. You have 4 different equations. Actually, every constant is different in there. So someone combined all of these equations into one equation that we call the ideal gas law. PV equals nRT. R is a new constant the ideal gas constant that combines all of the other constants in there. This one you do need to know. But I promise, any problem, if you know this equation, you can deduce the previous ones. Okay? Because you can see in here, for instance, the pressure and temperature are directly proportional. Pressure and number of moles, volume and number of moles. You can see that the pressure and the temperature are proportional. You can just make all sorts of combinations in there. Pressure and volume are inversely proportional, because when one increases, the other one decreases. This will tell you everything that we have discussed. You don't have to memorize 4 different equations, just memorize this one, and it will solve any problem. I promise you. One thing that's important, in this equation, the pressure is going to be in atmospheres. The volume is in liters, the number n is number of moles, temperature is in Kelvin, R is the ideal gas constant, 0.08206, liters times atmosphere times mole Kelvin. This number, as I tell my students, know it. It will probably be given to you in an exam, okay? I'll not take the chance because it's easy to remember. One of the things that my students always ask me is, do we always have to use atmospheres? Do we always need to use liters? I said, depends. Temperature in Kelvin, definitely. Okay? But as far as pressure and volume, sometimes you can change the units, sometimes you can't. When you're doing, what happens if I change the temperature, what happens to the volume? If I change the pressure, what happens to the temperature? Things like that. So sometimes it's okay, as long as you're consistent, and if you're going to give the volume milliliters, your answer will be milliliters. If you're using millimeters of mercury, the answer will be millimeters of mercury. But sometimes you can't. So the safest thing is always use the units. You don't want the day of the exam to be thinking, is it okay to change? It takes you just a moment to change milliliters to liters. It may take a few more seconds to change millimeters of mercury to atmospheres, but it's no big deal. So why take any chances? Okay? So the ideal gas law describes the properties of an ideal gas, but the question is, what is an ideal gas? And what are we assuming, how accurate that is to describe a real gas? Okay? So an ideal gas is, once again, a hypothetical construct. There's no such a thing as an ideal gas. But we can explain all of the observations we have made using the kinetic molecular theory that we're going to see later on. And it explains everything right. Now, we're assuming that all the gases we're dealing with are ideal, and your book tells you that's reasonable whenever you have low pressure or high temperature. Fact is, I want to be honest with you, the ideal gas law is accurate enough for almost anything you do in the lab. Okay? I remember I was teaching at a college. We was isolating hydrogen in the lab, and the answer for the volume came out in, I don't remember now, but we have it in liters. And then we say to the students, let's assume that this is what we calculate with the ideal gas law. Let's see how you adapt it if it was a real gas. There's some change you can do to this equation to explain, and we'll cover that in the next video, okay? So we actually did the calculations, and when we gave the answer with the correct number of significant figures, guess what? The answer was the same than before we made the corrections. Coincidence? Maybe, but at that college, we used to have anywhere between 800 and 1,000 students on a particular semester taking chemistry. We tried that as an experiment in all of the labs. So when over 800 students, you'll come up with it didn't make any difference, you start figuring like, there's something to it, okay? So in the next video, we are going to see how you change the equation for real gases, but let me tell you now, you can use the ideal gas law and you're going to get good results. So rather than trying to explain, I'm sorry, I touched something. I started. Okay. One of the things that I tell students when you're doing gas problems is first label everything very carefully, because when we write equation, you want to make sure that you are putting the right numbers in the right place and always get in the habit of changing the units, because I don't want to be worried, is it okay to change in this time or not? So always use the correct units. So this is a scuba tank, and the volume before anything happens, so I'm going to call it V1, is 13.2 liters. I don't need to make any change because already in liters. The pressure before anything happens is 153 atmospheres, correct units. The world temperature is 27 degrees, but I'm going to change it to Kelvin, so that's 300 Kelvin. Okay. Now, when the diver is at 70 feet below the surface, that's not part of the equation, so we're not going to worry. They say, what is going to be, how many liters? They're asking you for the volume underwater. When the pressure is 3.13 atmospheres. It's obviously the pressure in the tank was much higher because that's compressed air, but now the pressure that gets into the diver would be 3.13, and they want to know this would be the equivalent to what volume. Obviously, the temperature didn't change because they don't tell you. So T2, we're going to call it T1. So how do you solve these problems? You know only one equation, PV equals nRT. I always tell my students, put everything that changes on one side of the equation and everything that does not change on the other side. So we have volume and pressure changing. So it's already right. This is changing, this is not changing. So I can say that the P1 V1 before equal to equal P2 V2 because this number doesn't change. Now they're asking me for V2. So V2 is going to be P1 V1 divided by P2, and then just replacing V1 13.2 liters, P1 153 atmospheres, P2 3.13 atmospheres cancel, so we're going to get answer liters. Before I give you the answer, I always tell students, stop and think. Okay, the pressure has decreased. Do you expect the volume to increase or decrease? It's going to increase. The pressure has decreased a lot, so the volume is going to increase a lot. I like to always have an idea. Okay, so when I did these calculations, and I had three significant figures for all of these numbers, so I'm going to give you the answer with three significant figures, I came up to 651 liters. The original volume was 13.2, so yes, the volume did increase. By doing it this way, I know that it's very easy to reverse the pressure, but if I took the time to write P1, P2, and I read P1 is 153, P2 is 3.13, the chances of you making a mistake are much smaller. But in addition, you're predicting the volume is going to increase, and it did increase. If you have put them wrong, the volume would not have increased, so you know to go back till you have made a mistake. But once again, the point I'm trying to make is that if you know this equation, you can solve the problem. You don't need to memorize. We deduce the equation we're going to use in there. Let me do one other example where you have more things changing. Hot air balloon. Okay? So V1, the original volume of the balloon, is 225 liters. The pressure is 0.940 atmospheres. The temperature is going to be 25 plus 273, so that's going to be 298. 298 Kelvin. Okay, so the balloon starts going up. So the pressure the next pressure is going to be 0.990 atmospheres. The temperature obviously gets colder as you go up, so it's going to be 0 plus 273, so that's going to be 273 Kelvin. Okay? So what is the new volume? Now you can say this is more complicated because we are changing two different factors. That's perfectly okay. PV equals nRT. We're dealing with pressure, volume, and temperature, so I put everything that changes, PV. Now temperature is multiplying, so when I move it to the other side, goes dividing, equals RT. This is what changes, this is what remains constant. So I can say that P1, V1 divided by T1 equals P2, V2 divided by T2. Everything is given except for V2. So all you have to do is, okay, V2 is going to be P1 times V1 times T2 is going to pass multiplying, going to divide by T1, and P2 is going to go dividing to the other side. Replace all of these values. So 0.940 atmospheres times T2, 273 Kelvin. Oh, I forgot the volume, V1, sorry, 225 liters, divided by T1, 298 Kelvin, times P2, 0.990 atmospheres. And you see atmospheres cancels out, Kelvin cancels out, so it's going to give me the volume in liters. Everything looks good. Hopefully, by taking the time to making sure you put the right number in the right place, you're doing it right. But once again, you can predict, okay, the pressure is increasing. The temperature is decreasing. So what do you expect the volume to do? Well, when the pressure increases, I expect the volume to decrease. When the temperature decreases, I expect the volume to decrease, right? So we do the calculations in there, and I came up with 196 liters, which is less than the original volume. So once again, my volume decreased, so I know I did it right. Yes, you can memorize every possibility, but once again, why would you do that? Write the ideal gas law, put on one side everything that's changing in the problem, on the other side everything that's not changing, and from there you can deduce an equation like this one, and they always give you everything but one of the variables, and you can calculate that variable. They're extremely easy problems. Just after you do a couple of them, you realize they're all the same. In some would change the pressure, in others the volume. It doesn't matter. You're always going to have an equation where they give you everything but one, and they're asking you for the one. It couldn't be any easier, I promise. Now, we've seen that the volume and even number of moles are dependent on the pressure and the temperature. So at the beginning, there was problems because different people were working under different conditions, and then the results that one person was getting did not match the results somebody else get. So to be able to compare, they decide to set up a standard temperature and pressure, and we call it STP. That way, everybody work at the same temperature and at the same pressure, and the results from one lab to another were comparable. So standard temperature and pressure is going to be 273 Kelvin. I never use the decimals, okay? If you want to, you're welcome. Or 0 degrees Celsius and 1 atmosphere. And everybody works at the same temperature and pressure, so everybody gets same results. There's another advantage. Someone start calculating saying, okay, and you can do the numbers if you want to, but anytime you use this pressure and this atmosphere, the volume always comes up to 22.4 liters. It doesn't matter what the gas is. This is a number that you want to know because it's very useful, because you can do the problems the way I showed you before, just replace the temperature with 273, the pressure with 1, or you can just assume that the volume is going to be 22.4 liters because the problem tells you it's at standard temperature and pressure. It saves you a couple of calculations. You may not care much about it, but if you do the worksheet that I have for gases, I try to solve the problem both ways. One using the actual pressure and temperature, and another one using just this molar standard molar volume. That's the name for this 22.4 liters. And you realize you save yourself some calculations. Every time you do calculations, there's a chance of making a mistake. So if you can do less calculations, it's quicker, it's safer. So why wouldn't you do it? Okay. These properties have been used many times to identify gases, and I don't want to memorize any of these equations. This is just an example. You can measure in the lab the density of a gas, but if it's an unknown gas, you can use the density to identify the gas, and it's a very simple experiment. Okay, but you know densities must divide by volume. From the PV equals nRT, you can determine the number of moles, right? The number of moles could be PV divided by RT, so you know the number of moles. You know the mass of gas that you're dealing with. So if you divide the mass, how many grams, by the number of moles, that gives you the molar mass. And the molar mass will help you identify the particular gas. So the density is measured in the lab, the number of moles is calculated, the mass, whatever you decide to use for the experiment. Yes, you could have two gases that have very similar molar masses, but many times this is just good enough to identify the gas. Okay? Again, I don't want to go through the calculations. I just want to realize that you can use this equation to do a lot of things, okay? And you will have examples of this in the worksheet that I have for gases. So, would you like to get that worksheet? I promise I have put every possible combination, changing this or that, where you get lots of practice. Some problems just have stable conditions, and if you have this particular information, what is the volume, what is the pressure, others are going to be, this is changing, that is changing. Do you have only one characteristic changing, or two or three? I have a very, very extensive worksheet. If you like to get it, or if you have questions, remember the video description has a link to my Washington account. Make an appointment, and you will get that worksheet. And I will go over it with you.